This lecture is on the golden rectangle, the last topic that we covered in Chapter 4. The definition of the golden rectangle is a very simple one. It's any rectangle where the ratio of the length over the width is equal to phi. And of course, I hope you remember that phi is that irrational number that we met many times in Chapter 2, 1 plus the square root of 5 over 2. And if you see in your calculator 1.618033 and so on, that will be equal to, you can say that it's equal to phi. It's really a rational approximation, as you know, but we will accept that as being equal to phi. The most important thing to remember about this rectangle is that it has nothing to do with its size. In other words, one of you might draw a golden rectangle and it looks like this, or others may draw one that looks bigger than the one that was given to us. But notice that the overall appearance is the same. You can see that the ratio of length to width looks similar. Of course, by hand, I can't draw an exactly golden rectangle, but being golden does not mean anything about its size, only the ratio of its length to its width. Another way that you can actually define the golden rectangle is by the fact that if you cut off the largest square possible, that the rectangle that is left, it has the same proportion. In other words, it's golden. So if we look at this golden rectangle here, we know that L over W is phi. If we start with a golden rectangle, we know that the ratio of length to width is phi. If we cut off the largest square possible, which would be this blue square here, a W by W square, we're left with this white rectangle, which is also golden. So let's label its length by little l and its width by little w. And I will show you a more mathematical proof that little l over little w is also phi. But then I'll show you a way that I don't mind if you do it. And it's a much easier proof. So if you remember some algebra, and you please look at the first proof. Okay, so we want to start here by trying to find little l over little w. Well, little l is the same thing as the width of the larger golden rectangle, so that is equal to capital W. And this little w here, whoops, excuse me, this is moving. Little w, this distance here, is equal to big L minus w, because that was a square. So this distance here is w. It's a w by w square. So the width of the little white rectangle is big L minus w. Now, I'm going to divide the top and bottom by w. So I get 1 over, I'll divide L by w, and then w by w gives me 1. Well, I know that big L divided by w is phi, so this is 1 over phi minus 1. Or 1 over phi is 1 plus the square root of 5 over 2 phi minus 1. And I'm going to write that as 2 over 2 instead of 1. So you can see that this 1 plus the square root of 5 minus 2, we have 1 over the square root of 5 minus 1 over 2. and I would invert and multiply and get 2 over the square root of 5 minus 1. Now you can't see that that's equal to phi, but remember we can rationalize the denominator. And so let's multiply by the square root of 5 plus 1 over the square root of 5 plus 1. In other words, we're multiplying the fraction by 1. We're not going to change it, but we'll change the way it looks. So I'm going to multiply 2 times the square root of 5 plus 1. 2 times, and I won't multiply it out. You can if you want. And on the bottom, we have the square root of 5 minus 1, which is 4. Well, now I'll divide. Sorry about this. I'm having some trouble with the software. Dividing the numerator by 2 and the denominator by 2, we get the square root of 5 plus 1 over 2, which is phi. So if you remember how to rationalize denominators and some algebra, this would be the prettiest way of doing this proof. Another thing you might remember is from Chapter 2, we learned that phi is that number such that 1 over phi minus 1 is equal to phi. So this we learned in Chapter 2, but I don't expect you to remember that. So we'll do a more simple proof and one I think that you can easily do yourselves. These are both golden rectangles. In fact, they are identical golden rectangles. And what I want you to see here is that it doesn't matter what unit of measure I use. If I want to use this top one here, for some reason I want to call the width, let's see, what would that be? 1, 2, 3, 4. If I want to call this unit of measure right there 1, I can. And then I would say, well, if I want to do that, I know that the length over 5 is 1 plus the square root of 2. 1 plus the square root of 5 over 2. And I would then solve for L. And I could get the length is, by multiplying both sides by 5, I have 5 plus 5 radical 5 over 2. But who would want to do that when we can just call the width 2? In other words, down here, if I choose to use my unit of measure, half whatever the width is, then if the width is 2, the length is 1 plus the square root of 5. So my suggestion, I'm sorry you guys, my suggestion is to always, if you are given a golden rectangle, to call the width 2 and the length 1 plus the square root of 5. So if we do that in this case, and we want to cut off the largest square, all right, well, I guess that would be a 2 by 2 square, wouldn't it? Oh my gosh, I'm so sorry, I can't, there's something wrong with this. I would cut off this square here, and I want to prove that the smaller rectangle is golden. So I need to label its length and width. Okay, well, you know that the length is 2 because this distance is 2, and now we need this right here, this distance from here to here. I'm going to change color because of this mess. So that distance will be the long distance, 1 plus the square root of 5, minus the side length of the square, 2. And that is the square root of 5 minus 1. So we know that for this smaller of the rectangles, the one I'm shading in green here, that the length over the width will be L over W is equal to 2 over the square root of 5 minus 1. Now we saw that in the first proof, and I rationalized the denominator and came out with phi exactly. But I don't mind if you just put it into your calculator and get an approximation. And what you will get on your calculator, if you do this correctly, and I please practice it because you need to do it on the test to know how to put these numbers into your calculator, you will get 1.618033 and maybe a couple more digits. And you may say then that this is phi. So again, the suggestion is whenever you're given in a problem the fact that a rectangle is golden, go to that rectangle. You may have to draw a diagram, or maybe the diagram is given. Label its width as 2 and its length as 1 plus the square root of 5. Then go back to the problem and see what it's asking. This is a problem from our text. It says, suppose you have a golden rectangle cut out of a piece of paper. Stop. Okay, we have a golden rectangle, so go down and draw a picture of something that looks kind of like a golden rectangle. All right? And it's golden, so I'm going to label this 2, and I'm going to label its length 1 plus the square root of 5. Notice I haven't even looked at what the question is asking. Now I go back. Suppose you fold it in half along its base and then in half along its width. You have just created a new smaller rectangle. Well, in fact, we've created 4 smaller rectangles, haven't we? Let's put the dotted, oh boy. Well, this is really giving me trouble. We get the dotted lines across the middle here, and folding it along its width, we would get this. And so these 4 rectangles are all identical. And we want to know, is that rectangle golden? Well, it's not hard to do this because we labeled this as 2, so the width of the smaller one is half of 2, and the length of the smaller one from here to here is half of this length, which would be 1 plus the square root of 5. Half of it is over 2. Oh, well, the width is 1 and the length is phi. So the length over the width is 1 plus the square root of 5 over 2 over 1 if you want, which is 1 plus the square root, oh my gosh, 1 plus the square root of 5 over 2, which is phi. And you've proven the answer is yes, and you justified your answer. This problem we did in class, you take a golden rectangle, and since I'm having trouble with this software, I drew it there before I turned it on again. I drew a golden rectangle, and I better take my own advice. I want to call this 2, and this 1 plus the square root of 5. The length. Now it says, draw a circle, the largest circle inside it that touches 3 sides. And so you can see that I drew the yellow circle touching 3 sides. The circle will touch 2 opposite sides of the rectangle. If we connect those 2 points with a line and then cut the rectangle into 2 pieces along that line. Okay, so let's draw that line. I'll make that line green. Between the 2 opposite points. Okay, it should be going through the center there. We divide it into 2 rectangles. We divide it into this green one and this blue one. So then it asks us if we will either of these 2 rectangles, the green one or the blue one, will either of them be golden? Well, we have to know their length and their width. It's always the same thing. So let me stay in blue here, and we'll figure out the length and width of the blue one. The important thing to notice is that the radius of that circle, this length, this length, this is 1. So the radius of the circle is 1, and therefore the width of that rectangle is 1 here, and the width of this rectangle, the blue one, would be, well, the square root of 5, right? Because the total length is 1 plus the square root of 5. And then we know that the length of the small one is 2, and we're ready to go. So for the green rectangle, I have its length over its width. The length is 2, the width is 1. That is equal to 2.0, which is certainly not equal to phi, so the green rectangle is not golden. Now, let's do the blue. The length, let's see, which is bigger, 2 or the square root of 5? Well, the square root of 4 is 2, so the square root of 5 is 2 point something, and it's bigger. So for the blue one, we would have the length, square root of 5, over 2 is the width. And if you put this into your calculator, which I don't have next to me, you will get a decimal, which is 1 point something. 1 point something. But, because the square root of 5 is a little bigger than 2, yeah, but it will not be phi. You'll see it's not going to be 1.618. So you do that and make sure that you get 1 point something that is not equal to phi. Neither of them are golden. If you start with a golden rectangle and you attach the largest square you can, notice we're starting with, let's label that rectangle as rectangle A. Notice A is down here. So we attached a square to the longest side, and we got a larger rectangle. And I don't know what this is right here. This may have been a mistake in my writing these slides. Let's just ignore that. We take rectangle A and add a square to the longest side. Do we get a golden rectangle? Well, again, let's go to our rectangle A, the golden rectangle, and let's make the length 1 plus the square root of 5 and the width 2 from here to here. That's the one that we know is golden. Now we add a square. Well, the square is, one side is 1 plus the square root of 5, so all the sides are 1 plus the square root of 5. It's a square. 1 plus the square root of 5 is this length here. Now, what we want to know is golden is this rectangle here, A plus the square. So its length would be equal to 3 plus the square root of 5. And let's put it over its width, L over W. The width of the larger one there is 1 plus the square root of 5. This is the width and the length. Now put that into your calculator and you will get phi. Now we proved this for any golden rectangle. If you add a square to the longest side, you get another golden rectangle. So of course you could repeat the process, getting larger and larger and larger golden rectangles. What's amazing is that you don't have to start with a golden rectangle and attach squares. You can actually start with any rectangle and keep attaching a square to the longest side, and what you end up with, well, the further you go, the closer your large rectangle is to being golden. So let's keep a little tab up here of length by width, and you'll see what I mean. I'm going to start with a 1 by 6, and so I add a square, and that would be a 6 by 6 square, wouldn't it? So the length of the bigger one now is 7. 6 plus 1 and it is 6 wide. So we start with a length 6, width 1. The second one we get has length 7 and width 6. Okay, so now we attach a square. And change colors here so you can. We attach a square to the longest side. That would be 7. A 7 by 7 square. So now we have 13 is the length of the largest rectangle, and 7 is its width. So we have 13 by 7. You don't care if these are different colors. Okay, so we'll pick another color and add a square to the longest side of this rectangle. And so this would be a 13 by 13 square. So this was 7 and this was 13. So now our length is 20 and our width is 13. So we have 20 by 13. Let's see, we've got room to do one more. I won't run out of space. I'll add a square to the longest side. And this is a 20 by 20 square. So our rectangle is now, let's see, this was 20 and 13, so it is 33 in length, 33 by 20. So we have 33 by 20. Now if I were to again add a square, I can't because I ran out of space here, but if I again added a square, you would see that it would be a 33 by 33 square. So I would get then 33 plus 20, or 53. The next one would be 53 by 33. Now if you take 53 and divide it by 33, you will get something pretty close. It would be 1.61 something probably. I don't have my calculator, so let's just say 53 divided by 33 is not real close, but it's going to be close to phi. And the further you go, you get to a length over a width that is very close to phi. The length over width is approaching phi. Now, if you go back and look at problem number 10 in section 2.2, this problem told you that you could start with any two numbers and build a sequence, just the way that we built the Fibonacci sequence. And the ratio of terms to the one before it would go to phi, just like we know that the Fibonacci sequence, f sub n plus 1 divided by the one before it, that approaches phi. But it doesn't matter if you start with 1, 1. You could start with any two numbers and you will get this ratio of terms approaching phi. Well, notice what we did here. We started with 1 and 6. We added them to get 7. We added 2 to get 13. Then added 13 and 7 to get 20. Added 20 and 13, added 33 and 20. So this really is an example, a geometric example of problem 10 in 2.2. This slide, if you want to think more about that problem in 2.2 number 10, you could put it on pause here and notice that I did another example. If I started a sequence Sn, let's say with 1 and 3, then adding the terms, you get this sequence. And notice that if you go out to 19 terms, that the Fibonacci sequence, F19 over F18, we get pretty darn close to phi, and starting with 1 and 3, we also get very close to phi. This would be like starting a 1 by 3 rectangle and adding the largest square. It's just a geometric version of the same problem. This is another problem in the text. Consider a 10 by 10 grid. find the 4 points that when joined to make a horizontal rectangle, make a rectangle that is closest approximation to golden. Well, I think that the way to do this is just to think of the Fibonacci sequence. We know that fn plus 1 over fn, as n gets large, approaches phi. So we want to take our length as a Fibonacci and our width as the Fibonacci before it. The largest Fibonacci, less than or equal to 10, would be 8. So let's see, we would go, it would be this wide, and the one before it is 5. So 1, 2, 3, 4, 5. So I should have a different color here. This yellow rectangle is an 8 by 5. An 8 by 5. And I think that would be the closest to being golden. Of course, you could start a sequence with 1 and 2 or 2 and 2 and see if you would get a ratio that was closer to phi. But we're safe to stick with the Fibonacci's and take the largest Fibonacci less than 10 and then the Fibonacci less than that. We'll have a ratio the closest to phi in that 10 by 10 grid.